Today we're going to be talking about the sequential counting principle, which is the most important and fundamental way that we count the number of ways that something can happen. And we do that by breaking up the whole process into a sequence of choices where we can know how many options we have at each stage. And by knowing how many choices we can make at each stage, we can combine all that information together to know how many ways a particular thing can occur. Let me start with an example. At a particular diner, the farm breakfast is a breakfast dish, and it has three choices that you can make. And each of those choices involve a certain number of options. You can decide which way you want your eggs to be made. They can be over easy, they can be sunny side up, or they can be scrambled. So you have three different ways of ordering your eggs. You have two choices for your meat. You can have bacon with your breakfast, or you can have sausage with your breakfast. And then finally, you can get a slice of toast, and they have three different kinds of toast available to you. You can get white toast, wheat toast, or sourdough toast. And so what we want to ask is how many different breakfasts are possible? If you wanted to go to this diner and try all the different ways of combining together the options for a farm breakfast, how many times would you have to do that? So how many breakfasts are possible? So in order to figure this out, we can make a tree. And a lot of times making a tree of choices is a really good way of keeping track, visualizing what the possibilities are. Now, for some of the larger examples later on, a tree is going to be a little bit unwieldy, but for a relatively small case like this, it's a really good way of seeing what's going on, and the intuition we build here will help us as we go forward. So the way that we could think of this process is making three choices in sequence. We need to choose what eggs we're going to get, we need to choose what meat we're going to get, and we're going to choose what toast we're going to get. And every time we make one of these changes, we go down a new path. So we're going to say that when we choose our eggs, we've got our three different possibilities here. And I'm just going to label these with O, SU for sunny side up, and SC for scrambled, so that we can keep track of which one is which. And there are three different ways that we can have our eggs. Now we need to choose our meat. And importantly, no matter which one of these egg paths we went down, we always have the same number of choices for meat. We always have either bacon or sausage. The previous choice doesn't affect the later choices that we have. So we can have bacon or sausage, bacon or sausage, bacon or sausage. And then finally, we can select what type of toast we want. And we've got three different choices for toast. So whether we chose over easy with bacon, we have our three choices here. Or if we chose over easy and then sausage, we'd have three choices. And in any of the other cases, we still have three choices. And so as you can see, the number of possibilities starts expanding quite significantly. And so we want to know, well, how many different ways are there to make this breakfast following all of these possibilities? And we can, of course, figure that out by drawing this tree and just counting up how many different options we have over here. So this first top choice might be the one where we choose over easy, bacon, and white as our choices for the meal. Then the next one is over easy, bacon, and wheat. And then we have over easy, bacon, and sourdough. And we could continue this down. And if we counted them all up, we'd find that there are a total of 18 choices here. But we, of course, want a more systematic way of doing this. We don't want to have to count up the number of leaves we get on these trees every time we make a decision, especially if we start considering possibilities where we have lots of decisions to make or lots of choices that we could have, lots of options that we could choose from at each stage. So what we can do instead is we can look at things in stages and say, well, if we were to stop the process partway through, how many would we have? And so if we were to stop after one choice, if we just chose the number of eggs that we, the type of egg that we are going to eat, we'd have three choices, of course, because we have three different selections that we could make for our eggs: over easy, sunny side up, or scrambled. But then once we make each of those choices, each one of those choices leads into two more choices in here, where each of our three choices corresponds to two possible meat choices that we have here. And so if we count these up, we can see that if we pause after our second choice, we have 1, 2, 3, 4, 5, 6 different breakfasts we could make, just considering the eggs and the meat. And so we have 6 choices at this point, but that comes from the fact that we made 3 choices for our first, 3 options for our first choice and 2 options for our second. And every choice, every option in the first choice led to 2 different options in the second. And each of those combinations gives us a different result. So we have 6 different possible egg and meat combinations. And then we can go one step further. And we can say, well, of these 6 egg and meat combinations, each one of them leads into 3 more possible options of our toast, white wheat, or sourdough. And so, following the same line of logic out here, we should have the 6 possibilities that we had before times 3 possibilities of toast for each one of those 6 to give us the 18. And that matches up with the picture that we've drawn so far of the tree, and we get that 6 times 3 is 18. But remember, this 6 came from the 3 times 2 from before. The 6 is the number of egg and meat combinations, which is in fact the number of egg options times the number of meat options. And so what we find is that the total number of breakfasts we can make here is 3 times 2 times 3. The number of options in the first choice times the number of options in the second choice times the number of options in the third choice. And this is demonstrating the sequential counting principle. When we make a number of choices in sequence, one after another, or if we can arrange our problem in such a way that it makes sense to consider a sequence of choices, then we can count the number of total ways of making all those choices by multiplying together the number of options at each stage. And this is indeed the sequential counting principle. So let's go ahead and state that. The sequential counting principle says that the number of ways to make n choices where the first choice has, I'll say, A1 options, A1 different things you can make for your first choice. The second has A2 options, and so forth and so on. The third one has three options, all the way up to the last one, the nth, I should say. The nth and last choice has n options, is the product a1 times a2 times a3 all the way up to an. So you multiply the number of options you have at each stage together, and that big product that you get by multiplying them all will tell you the total number of different outcomes you could get from making all these choices in sequence. And the picture behind this is exactly the same picture that we just had for the farm breakfast. We've got this tree that we can make where we've got a bunch of different choices, a bunch of different options for our first choice, where we have A1 options for our first choice, and then we've got some number of options for our second choice. And importantly, each one of these options in the first choice lead to the same number of options in the second choice. So that's a key point that I want to point out. That every option in the first choice leads to the same number of options in the next choice, and so forth and so on. If you're in a situation that's more complicated than this, where depending on the choice you make in the first step, you might have more or fewer options in the second choice, the sequential counting principle doesn't apply here. You'll need to handle things more carefully, maybe more directly. You'll need something more complicated. But in many ways, the sequential counting principle will work for many of the problems that we want. Although we'll see a little bit of a wrinkle in our last example today. So let me work with a few more examples. The first one is important because it's different from our first example. In our first example with the farm breakfast, every choice that you made had exactly the same options, no matter what options you had made in the previous choices. That's not always true. That's not always the case when we apply the sequential counting principle. What we care about is that there are the same number of options no matter what choice you made in the first choice. So let me take an example demonstrating that. Let me ask, how many ways are there to draw two cards from a 52 card deck in order? Now, this in order here means that we're going to care about what order we draw things in. We're going to consider drawing an ace of spades and then a king of spades different than if we drew a king of spades and then an ace of spades. For the sequential counting principle, we count those two options separately. We will see in a later lesson how to handle situations where the order in which you choose things doesn't matter. But let's go ahead and consider this. We can set up this problem as a sequence of two choices, where we ask, essentially, how many ways can we choose one card from the deck, and then we will choose another card. And these two choices form the two choices in our sequence. And so if we can count how many options we have in each choice and multiply them together, we'll get our answer. So for choice 1, where we're drawing the first card off the top, we ask, well, in how many ways can that happen? Well, there are 52 cards in the deck, and any one of those could be on the top. So for choice 1, there are 52 possible options, which could occur. We could have any one of the 52 cards at the top. Now, for choice 2, importantly, the exact cards that you could draw in your second draw, when you make your second choice of which card comes out, depends on what you chose in the first choice. So if you draw a card and it's the Ace of Spades, well, then there's certainly no possibility that you're going to draw the Ace of Spades again. But if your first draw is the Ace of Hearts, well, then the Ace of Spades is a possibility for your second draw. And so the exact options that are possible for your second draw depend on what your first one was. However, essentially, the number of options doesn't change. So if you draw one card, you have 52 different options. And then when you go to draw your next card, you will have 51 options, no matter what that first card you drew was. So there are 51 options, no matter what card you drew in step 1. So, by the sequential counting principle, which I will from now on abbreviate as SCP to avoid writing it out every time, by the sequential counting principle, the number of ways to draw 2 cards in order is 52, the number of choices for the first card, times 51, the number of choices for the second card. And so this we can throw into a calculator and find that we get 2,652. So there are 2,652 ways of drawing one card and then drawing another card, where you keep track of the order in which you drew them. All right, let's see another example where we have more choices to make, but fewer options in each one of the choices. Let me ask, how many 10-digit phone numbers are there? Now, if I just ask this question, this would be a little bit too easy. So let's impose some realistic restrictions on this, because not every conceivable phone number is actually going to show up. So let's ask, how many 10-digit phone numbers are there if the area code, which is the first 3 digits, we'll write that out in a second, cannot begin with 0, and the 7 digits after the area code cannot begin with 0, 1, or 9. Now, the reasons why things like this might be special is that whoever is making these decisions about phone numbers might want to keep numbers that start with 0 reserved special. Only special numbers are going to use those, like numbers that get you a hold of the operator, someone to help out with things like this. You also might not allow your numbers to start with 9 because your emergency number, 911, might start with 9, and you never want someone to be accidentally calling 911 if they don't need it, or you don't want it to be the case where someone accidentally has a number that includes 911 at the beginning, because then they'd never get a call. So this is a very common type of restriction that we'd have here. Now, a lot of times it's helpful with these sequential counting principle problems to draw some sort of diagram. If you can visualize what's going on, if you can write down your choices left to right, if you can say, okay, here's the place where we make this choice, then this choice, then this choice, a lot of times that helps you to organize your thoughts. So that's what we're going to do here. We're going to look at the structure of a phone number. And we're going to say that we're going to start with 3 digits for the area code. And then we're going to have 7 more digits, which are usually written in a group of 3, then a group of 4. And now what we want to record in each one of these slots here is the number of options for each one of these digits. Now, a phone number can accept digits from 0 to 9, so that's 10 possible digits that most of these positions can take. However, some of them are more restricted. So there are 10 digits for most spots in the phone number, but some are more restricted. So let's go ahead and fill those in. So in the area code, we're told that the area code can't begin with 0. So we can't have a digit of 0 here, but we can have the digits from 1 to 9. So that means that there are 9 choices for the first number in the area code, the first digit in the area code. Now, there are no more restrictions on the second and third digits in the area code, so there are 10 possibilities for the second digit, 10 possibilities for the third digit. Now, for the remainder, for the 7 digits that come after the area code, we're told that the first digit here can't be 0, can't be 1, and can't be 9, which means it can only be the digits from 2 through 8, and there are 7 of those, 2, 3, 4, 5, 6, 7, and 8. So there are actually only 7 options for the first number of the 7 that come after the area code, but the rest of the digits can be any of the 10 digits from 0 to 9. So we could imagine constructing a phone number by making an explicit sequence of choices. We're going to choose the first number, the second number, the third number, and so forth and so on. And at each step, we will have some number of options, usually 10, but with some restrictions elsewhere. So, by the sequential counting principle, the number of phone numbers under these rules is 9 times 10 times 10 times 7 times 10 times 10 times 10 times 10 times 10 times 10. I'm going to simplify that a little bit. I'm going to write that as 9 times 7 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 8. So this will be 9 times 7 times 10 to the 8th. Now 9 times 7 is 63, and then multiplying by 10 to the 8th means that we add on 8 zeros at the end of it. So 10 to the 8 is 1 followed by 8 zeros. So 9 times 7 is 63, followed by 8 zeros, which means that we have 6.3 billion possible phone numbers using this collection, using this set of rules. Importantly and interestingly, this means that this setup of area code with 7 digits afterwards with these restrictions do not allow for enough phone numbers to give everyone on Earth a phone number. There are over 7 billion people on Earth, and so these rules wouldn't give enough phone numbers. This is why additional things are added, such as area code, country codes, which behave like area codes, but for countries, and adding a few more digits on will give us more possibilities. Indeed, if we just went from a 7-digit phone number to an 8-digit phone number after the area code, that would multiply our number of possible phone numbers by 10. We'd get up to 63 billion. And so adding just the one extra digit can give us a whole lot more wiggle room when it comes to assigning phone numbers. All right, let's look at one last example, and this one's going to be a little bit more complicated. We're going to have to break it up a little ways. We're going to have to apply the sequential counting principle a couple of different times and be a little clever about it. So let's look at the following example. How many license plates are possible in the pattern LLLNNN, where L is a letter in American English, so 26 different letters. N is a digit, so just like for the phone numbers, 0 to 9. And there are 30 forbidden letter combinations. So one thing that people who decide these things about license plates and things like this have to take into account that if you just allow for random letters to go in there however you want, occasionally you get a letter that, or a sequence of letters rather, that is accidentally rude, that's accidentally offensive. If you just allowed all the possibilities. So it's very common in situations like this for there to be just forbidden combinations. They'll go through and they'll decide, oh no, that looks like a bad word, that looks like a bad word, that's offensive, we don't want to do that. And so they're going to allow most of the combinations of letters, because most of them are just nonsense, but there's going to be some forbidden letter combinations. Now, what's important here that we can see is that this 30 here doesn't directly tell us how many choices we have for the first letter, the second letter, or the third letter. In fact, if we try starting off the same way that we did the last problem, and we just say, all right, well, we're going to have 3 letters followed by 4 numbers, we've got a problem. Because there are certainly going to be 26 possible choices for the first letter, and then 26 possible choices for the second letter. But then the number of possibilities for this third letter is going to be different. Sometimes it's going to be 26, but sometimes it's going to be lower because these first 2 terms were the first 2 letters in a forbidden sequence, in a forbidden letter sequence, and so we can't allow that. We aren't told what the forbidden letter sequences are. We're just told that there's 30 of them. So we need to get a little bit more clever with this, and we're going to break this up into larger chunks and then handle each one separately. So rather than doing this, rather than just treating it as a sequence of 7 choices where we have a certain number of options for each one, we're going to go about it differently. We're going to do this a different way. We're going to compute this as follows. We're going to take the number of letter combinations that are allowed times the number of number combinations that are allowed. We're actually going to treat this as a sequential counting principle problem where there are only 2 choices to make. Which letter combination are we going to use? And then which number combination are we going to use? But then we're going to use the sequential counting principle to figure out what each one of these numbers are. So we're going to break our problem up into two smaller ones where we can figure out each one using the principles that we have at hand. So let's consider the letter combinations. So if we looked at the letter combinations with no restrictions, if we just allowed all of the letter combinations that we could possibly have, then by the sequential counting principle, there would indeed be 26 times 26 times 26 different letter combinations. This many ways of selecting 3 letters in a row. And it turns out that that gives 17,576. There are 17,576 ways of selecting 3 letters in sequence. However, some of those are forbidden. So there are 30 forbidden sequences out of these 17,000 and so forth. So there are 17,576 minus 30, which is 17,546 allowed letter combinations. So what we did in this case is we used the sequential counting principle to figure out how many letter possibilities there were total, and then we just subtracted off all the ones that we know aren't allowed. So there are 17,546 allowed letter combinations. Now, for the number combinations, this is easier because there aren't any forbidden number combinations. So we got number, and there are 10 possibilities for each of these numbers in the license plate. So all together, that's 10 times 10 times 10 times 10, it's 10,000. So there are 17,546 allowed letter combinations, taking into account the forbidden ones. And there are 10,000 number combinations, which means that the total number of license plates possible is going to be the total number of allowed letter combinations times the number of number combinations in the license plate, which will give us 1, 7, 5, 4, 6, and then 4 zeros afterwards, giving us 175,460,000. So we could license up to 175,460,000 cars using this pattern before having to get a new one, and making sure that none of those 30 forbidden letter sequences ever came up.